A quad tree is a type of tree data structure used for spatial partitioning. It efficiently represents two-dimensional spaces by recursively subdividing them into four quadrants or regions. This structure is commonly used for managing large amounts of spatial data, such as in image processing, computer graphics, and geographic information systems, GIS. For more tech interview materials, please go to our website at bowz8.com. Basics of a quad tree. Definition: a quad tree is a hierarchical data structure where each internal node has exactly four children. Structure: root node represents the entire 2D space. Subdivisions: each node subdivides into four equal regions, quadrants, if it contains more data than can be efficiently managed. Leaf nodes: nodes that do not need further subdivision because they meet certain criteria, e.g., contain a single data point. Subdivision rule: when a region exceeds a defined capacity, e.g., too many points or too much detail, it splits into four children. Top left, NW. Top right, NE. Bottom left, SW. Bottom right, SE. How quad tree works. Example: imagine you have a 2D space containing points. Here's how a quad tree processes the data. 1. Start with the entire space. The root node represents the entire 2D space. 2. Insert data points. Points are added to the root node. 3. Subdivision: when the number of points in a node exceeds a specified limit, e.g., 4 points, the node is subdivided into four quadrants. 4. Distribute points. Points are redistributed to the appropriate quadrant, child node, based on their coordinates. 5. Recursive process: the subdivision continues until each node contains a manageable number of points. Applications of quad trees include: 1. Image processing. Image compression: quad trees simplify images by representing uniform regions with single nodes. Region representation: efficiently store and process large bitmap images by segmenting regions of similar colors. 2. GIS. Spatial indexing: quickly find and manage spatial data, e.g., maps, locations. Point querying: identify which region a point falls into, e.g., determining a city within a map. 3. Computer graphics. Collision detection: in 2D games, quad trees help quickly check for objects that might collide. Frustum culling: improve rendering performance by identifying visible regions to draw. 4. Spatial databases. Efficient data storage: store large spatial datasets with quick access and retrieval. 5. Robotics. Pathfinding: divide maps into regions for efficient path planning. Advantages are: 1. Efficient search: speeds up querying spatial data by narrowing down regions. 2. Adaptive subdivision: subdivides only regions with high data density, optimizing storage. 3. Hierarchical representation: provides a clear way to organize spatial information. Limitations include: 1. Imbalanced trees: data clustered in certain areas may lead to uneven subdivisions. 2. Overhead: managing subdivisions and pointers can add complexity. 3. Not ideal for dynamic data: frequent insertions and deletions can be inefficient. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com. An R tree, rectangle tree, or region tree is a type of spatial data structure optimized for indexing multidimensional data, such as points, lines, rectangles, and polygons. It is particularly useful for managing spatial queries like finding the nearest neighbor or identifying objects within a given region. For more tech interview materials, please go to our website at bowz8.com. Basics of an R tree. Definition: an R tree is a balanced tree, similar to a B tree, used for spatial indexing. Each node in an R tree represents a bounding rectangle that contains one or more data points or child nodes. Structure: root node, the topmost node containing references to child nodes. Internal nodes, non-leaf nodes that contain bounding rectangles and pointers to child nodes. Leaf nodes contain actual data entries, e.g., rectangles, points, or references to the spatial data. Bounding rectangle, A bounding rectangle is the smallest rectangle that completely encloses all the data points or child nodes within it. How an R tree works. 1. Insertion. Locate a leaf node. Find the appropriate leaf node where the new data entry should be inserted. Minimize overlap. Choose the bounding rectangle that requires the least expansion to accommodate the new entry. Split. If a node exceeds the allowed capacity, e.g., for entries, split it into 2 nodes and propagate the split upwards if necessary. 2. Search. Traverse the tree. Starting from the root, check each bounding rectangle to see if it intersects with the query rectangle. Check leaf nodes. Once the relevant leaf nodes are reached, compare the data entries to the query criteria. 3. Deletion. Find the entry, locate and remove the data entry from the leaf node. Adjust bounding rectangles. Update parent nodes to reflect changes. Rebalance. If a node becomes underfilled, merge it with neighboring nodes to maintain balance. Applications of R trees include 1. Geographic Information Systems, GIS. Spatial queries. Efficiently query maps to find regions, roads, or landmarks within a specified area. Route planning. Quickly identify paths or neighboring locations. 2. Database systems. Spatial indexing. Used in databases to store and retrieve spatial data like coordinates or geometric shapes efficiently. 3. Computer graphics. Collision detection. Identify overlapping objects in 2D/3D environments. Rendering. Optimize rendering by determining visible regions in complex scenes. 4. Nearest neighbor search. Quickly find the closest data points to a specific location, e.g., finding the nearest restaurant or gas station. 5. Robotics. Pathfinding helps robots efficiently plan paths by managing spatial obstacles. Advantages are 1. Efficient spatial querying. Handles range and nearest neighbor queries efficiently. 2. Balanced tree structure. Similar to a B tree, ensuring predictable search and insertion times. 3. Dynamic updates. Supports frequent insertions and deletions without requiring a complete rebuild. Limitations include 1. Overlapping regions. Bounding rectangles and internal nodes may overlap, which can slow down search performance. 2. Complex splitting. Node splitting algorithms can be computationally intensive. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com. A Merkle tree is a data structure commonly used in cryptography, blockchain, and distributed systems to ensure data integrity and security. It's a type of binary tree where each leaf node represents a hash of data blocks, and each non-leaf node represents the hash of its child nodes. For more tech interview materials, please go to our website at bowz8.com. Structure of a Merkle tree. A Merkle tree consists of leaf nodes. These contain the hashes of individual data blocks, e.g., transactions. Non-leaf nodes, intermediate nodes. Each node stores the hash of the concatenation of its child node's hashes. Root node, Merkle root. The topmost node contains a single hash summarizing the entire tree. How a Merkle tree works. Hashing data blocks. Each piece of data, transaction, or file segment is hashed individually to create leaf nodes. Combining hashes. Pairs of hashes are combined and rehashed to form parent nodes. This process continues up the tree until a single hash, the Merkle root, is produced. Verification. To verify if a specific data block is part of the tree, you only need a subset of the hashes, a Merkle proof, instead of the entire dataset. This significantly reduces computational effort and bandwidth. Applications of Merkle trees include 1. Blockchain, e.g., Bitcoin, Ethereum. Efficient transaction verification. In Bitcoin, transactions in a block are organized into a Merkle tree. The Merkle root is stored in the block header. Nodes can verify transactions using Merkle proofs without downloading the entire blockchain. Data integrity ensures that blocks have not been tampered with by verifying that the Merkle root matches the original data. 2. Distributed file systems. IPFS, interplanetary file system, and use Merkle trees to verify the integrity of files and track changes efficiently. 3. Certificate transparency. Google's Certificate Transparency project uses Merkle trees to detect fraudulent or misissued SSL/TLS certificates. 4. Peer-to-peer networks. BitTorrent and similar networks use Merkle trees to verify the integrity of file chunks during downloads. 5. Databases. Some NoSQL databases, e.g. Cassandra, use Merkle trees to quickly compare data across distributed nodes and resolve inconsistencies. Advantages of Merkle trees are: 1. Efficient verification. You can verify data integrity without needing the entire dataset. 2. Scalability. Suitable for large datasets because the hash size remains constant regardless of data size. 3. Tamper detection. Any change to a data block changes the corresponding leaf hash, propagating the change up to the root. 4. Bandwidth savings. Only a small set of hashes is needed for verification, Merkle proofs. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com. An LSM, log-structured merge, tree is a data structure optimized for write-heavy workloads, commonly used in databases and storage systems. It balances fast writes with efficient read performance and is particularly well-suited for systems where large volumes of data are frequently inserted or updated. For more tech interview materials, please go to our website at bowz8.com. An LSM tree consists of two primary components. 1. In-memory structure, usually a memtable. A fast, mutable data structure, like a balance tree, that holds incoming writes temporarily. When the memtable reaches a certain size, it is flushed to disk. 2. On-disk structures, SSDables, sorted string tables. Immutable, sorted files that store the flushed data. These files are periodically compacted and merged to optimize performance and reduce storage fragmentation. How does it work? 1. Write operation. New data is written to the memtable and appended to a write-ahead log, WL, for durability. 2. Flush to disk. Once the memtable is full, it's flushed to disk as a new SSDable. 3. Compaction. SSDables are periodically merged and compacted to maintain efficiency and prevent too many small files from accumulating. 4. Read operation. To find data, the system checks the memtable first, then searches the SSDables in order of recency. Key characteristics of LSM trees include: 1. Write optimized. Writes are batched in memory, making them very fast. 2. Immutable disk structures. SSDables are immutable, avoiding the need for in-place updates and reducing write amplification. 3. Compaction. Periodic merging and compacting of SSDables maintain efficiency, reducing the number of files to search during reads. 4. Read performance trade-off. Reads can be slower because data may be spread across multiple SSDables, but techniques like Bloom filters and caching help mitigate this. Applications of LSM trees include: 1. NoSQL databases. Apache Cassandra uses LSM trees to handle high-throughput write operations efficiently. LevelDB by Google, a key-value store optimized for reads and writes. RocksDB by Facebook, an advanced version of LevelDB optimized for server workloads. 2. Search engines. Elasticsearch uses LSM-like structures to index documents efficiently. 3. Time series databases. InfluxDB and TimescaleDB use LSM trees for fast insertion of time series data. 4. Message queues. Apache Kafka implements LSM-like mechanisms to handle large volumes of log writes. 5. File systems. Some file systems, like log-structured file systems, LFS, use LSM-inspired designs to optimize disk writes. Advantages of LSM trees are: 1. Fast writes. Ideal for applications with high write throughput. 2. Efficient disk usage. Sequential writes to disk reduce disk I/O and latency. 3. Durability. Data durability is ensured via the write-ahead log, WL. 4. Scalability. Compaction helps manage large datasets by keeping storage efficient. Challenges of LSM trees include: 1. Read amplification. Data spread across multiple SSDables can slow down reads. 2. Write amplification. Multiple compaction processes can increase the total amount of disk writes. 3. Compaction overhead. Compaction consumes CPU and I/O resources, which may impact system performance. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com. A B tree is a self-balancing search tree designed to efficiently manage large datasets by minimizing disk I/O operations. It is widely used in databases and file systems for indexing and searching large amounts of data. Here's a quick breakdown of how it works and where it's applied. For more tech interview materials, please go to our website at bowz8.com. Structure of a B tree. A B tree of order M has the following key properties. Nodes can contain up to M-1 keys and M children. Balanced structure. All leaf nodes are at the same depth. Sorted keys. Keys within each node are sorted. Child nodes. The pointers, or references, to child nodes ensure that the values are split between the keys in an ordered manner. Each key divides the data space, and the children represent values that fall between the keys. Operations in a B tree. 1. Search. Start from the root node. Compare the target value with the keys in the node. Follow the appropriate pointer to a child node based on the comparison. Continue until you find the key or reach a leaf node. 2. Insertion. Insert the key into the appropriate leaf node while maintaining the sorted order. If the node exceeds capacity, M1 keys, it splits into 2 nodes. The middle key is promoted to the parent node. If the parent node exceeds capacity, the process repeats up to the root. 3. Deletion. Delete the key and adjust the tree to maintain balance. If a node becomes too small, less than M/2 keys, it borrows keys from or merges with neighboring nodes. Applications of B trees include 1. Databases. Indexing. B trees help efficiently search, insert, and delete records in large databases, e.g., MySQL, Oracle. Primary and secondary keys allow quick lookups and range queries. 2. File systems. NTFS, Windows, and HFS Plus, macOS, use B trees to manage directories, file metadata, and file paths. Fast lookup of file names in large directories. 3. Search engines. B trees index web pages or search results, enabling fast data retrieval. 4. Networking. Routing tables, used to manage large routing databases efficiently. 5. Memory management. Operating systems use B trees for tasks like virtual memory paging. Advantages of B trees are 1. Balanced structure. Ensures that operations have predictable O, log n complexity. 2. Efficient disk access. Designed to minimize disk I/O by storing multiple keys per node. 3. Scalability. Handles large datasets by keeping the tree height small. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com.